In this video, I'll be discussing an interesting visual proof of the Fundamental Theorem of Algebra. This is an important theorem that gives us insight into polynomials. Polynomials are equations involving powers of x, such as y equals x minus 4, or 2x squared plus 3, or x to the fourth plus 8x cubed minus 2x. One of the common problems with polynomials is to find the inputs that give 0 as an output. These inputs are called roots. Let's start with the polynomial on the top. We can solve for x by adding 4 to both sides, and then we see that 4 equals x. 4 is a root of this polynomial. Now we solved this algebraically, but we could have also done it visually. If we graph using an x and y axis, y equals x minus 4, this is the point where y equals 0. Again, we see 4 is the root. 4 is the input that gives us 0 as an output. And this equation, x minus 4, is called linear. We see in the graph this is just a straight line. And that's because it has just x. There are no higher powers. If we have an equation with a higher power, such as x squared minus 2x minus 3, it's no longer linear. We get a curve. And here we see there are two roots, -1 and 3. And we can use these two roots to write the polynomial in a different form. X squared minus 2x minus 3 is equal to x minus -1, our first root, times x minus 3, our second root. And this form on the right is called the linear factorization of the polynomial, since both of these terms are linear. They just have x and no higher power. We could do the same thing with an even higher power. Now we have x to the third power, and graphing this, we see there are now 3 roots, -2, 0, and 3. And again, we can use those roots to get a linear factorization, and this continues more generally. If we have a degree 4 polynomial, x to the fourth plus some other stuff, we will get 4 roots, which gives us a linear factorization involving those 4 roots. And any degree n polynomial will give us n roots and a linear factorization with n terms. And this is the fundamental theorem of algebra. Every nth degree polynomial has n roots. And this is a very important result, but there are a few caveats that we should cover. Let's look at the equation y equals x squared. This is degree 2, so we should expect 2 roots. But when we graph, we only see 1 root at 0. And this equation does have 2 roots, but they are both 0. This is our linear factorization. So every nth degree polynomial has n roots, but they're not necessarily distinct. Some of them might be repeated. Next, let's look at x squared plus 1. There doesn't appear to be any roots. The output is never 0. And that's because we're just looking at the real numbers. The roots of this polynomial are I and -I, which give us this linear factorization. So the fundamental theorem of algebra is not a theorem about the real numbers. It holds within the complex numbers. Within the reals, every nth degree polynomial has at most n roots. They might not have n, but they can't have more. Suppose we have a polynomial p that has k roots. Well, then p is divisible by this linear product using those k roots. There are k terms, so this product has degree k. And since p is divisible by this, p must have degree at least k. So k, the number of roots, can't be greater than the degree of p. If p is an nth degree polynomial, it has at most n roots. Again, within the reals, it might have less. It's only once we move up to the complex numbers that every nth degree polynomial has exactly n roots. So we want to work with the complex numbers, but they're harder to display. In order to graph in the typical way, we would need 2 dimensions for an input, and then another 2 dimensions for an output, giving us a 4-dimensional graph. But we can't do that. Instead, we'll graph both the input and the output on the same two dimensions. So we'll show the input, some point x, in pink, and then the output, our polynomial p of x, in blue. When the polynomial is x, these are just equivalent, so the points are in the same spot. If we add a constant, such as x plus 1, the output is now shifted 1 to the right. Or with x minus 1, it's shifted 1 to the left. And we see similar things with other constants, like x minus I, or x plus 3 minus 2i. We can also add a coefficient onto x. The polynomial 2x gives us an output that is twice as far from 0 as the input, whereas 0.5x gives us the output that's half the distance. So now we have a way to graph these points. Let's use this to prove the fundamental theorem of algebra. Every nth degree polynomial has n roots. But this isn't the only form of the fundamental theorem. You may also see it stated as every polynomial has at least one root. And this is equivalent, and it's going to be easier to prove. But first, let's just make sure that it's equivalent. So we want to see that if every polynomial has at least one root, that implies that every nth degree polynomial has n roots. And we'll do that using induction on n. The case where n is 1 is pretty straightforward. As we saw before, a first degree polynomial has at most one root. But above we see it has at least one root, so it must have exactly one root. So now let's look at n. Suppose p of x is an nth degree polynomial. It has at least one root, so let's say r sub n is a root of p of x. Now we can divide p by x minus r of n to get another polynomial, q. Now we'll multiply on both sides by x minus r sub n. These will cancel out, and so we're left with p equals q times x minus r sub n. And we want to notice that q is degree n minus 1. And so by our induction hypothesis, it has n minus 1 roots. And so p has n roots. It has the n minus 1 roots from q and the extra root r sub n. So the fact that every polynomial has at least one root implies that every nth degree polynomial has n roots. And these two statements are equivalent because we can pretty easily go the other way. If an nth degree polynomial has n roots, then it does have at least one. So the bottom definition gives us a more interesting result, but we only need to prove the top definition. Every polynomial has at least one root. So going back to our visualization, given some polynomial p, we'd like to show that there's some input that sets our output to 0. But instead of just looking at one point at a time, we'll look at a bunch of points. So let's take our input to be the unit circle, all of the points that are distance 1 from 0, and we'll label that as u. Just as with the individual points, when the polynomial is x, we get the same input and output. We get the same circle. Adding a constant will move the output around, and then adding a coefficient will change the size of the output. But things get really interesting when we go to a higher power. Let's look at x squared. It appears that the input and the output are the same. We're just getting the same circle. But let's actually draw these out. As we draw the input around the circle, we see the output is moving twice as fast. Once the input has made one lap around 0, the output has made 2. So we can distinguish these two with what is called the winding number. U has a winding number of 1 because it goes around 0 one time. But u squared has a winding number of 2 because it goes around 2 times. And u cubed has a winding number 3. U to the 4th has a winding number 4, and u to any n has a winding number of n. As we raise the power, we go around 0 more times. Now to clarify our understanding of the winding number, let's look at some more examples. With u plus 2, the winding number is 0. This is a circle, but it's not actually going around 0, so the winding number is 0. And here, the winding number is 1. We're making 2 loops, but only one of those loops goes around 0. And what we want to notice is that if we continuously change the polynomial, the winding number doesn't change. If we move from any p of u to any q of u continuously, then the winding number of p and q must be the same. It will not change. Unless we pass through 0. Here we started with a winding number of 1, and we can change to a winding number of 2 if we pass through 0. The winding number describes how many times we go around 0, but if we pass through 0, that question doesn't really make sense. In this case, the winding number is undefined, so we can jump from one winding number to another by passing across this undefined point. For another example, let's start with x plus 1.5, which has a winding number of 0. Now we'll increase the coefficient on x, and the winding number remains 0 until we hit 0. At this point it's undefined, and then when we continue to increase, we now get a winding number of 1. So passing through 0 gives us a way to change the winding number, and in fact it's the only way that the winding number can change. And this idea is important because it tells us that if we go from p to q continuously, but the winding number of p and q are not the same, then we must have passed through 0 at some point. There must have been some polynomial f between them that had a root. There's some r that set f to 0. So this gives us a method by which we can identify a root. But there's a slight problem. This method tells us that there is some polynomial f, but we don't necessarily know what it is. We want to show that every polynomial p of x has a root. We want to be able to target a specific polynomial. But this comes down to just a change in our perspective. In this example, we kept our input fixed as u, the unit circle, and we continuously transform the polynomial from x plus 1.5 to 2x plus 1.5. But we could instead think of keeping the polynomial fixed as x plus 1.5 and continuously transforming our input from u to 2u. The output is the same, we get the same exact result, it's just a different way of thinking about this. But this change in perspective is important because now we know there is a root for this polynomial, x plus 1.5. So now let's just modify this technique to work for any polynomial. In the previous example, we transformed our input from u to 2u, and that worked because our root was in this donut shape. But that won't hold for all polynomials. We can instead transform from 0u to infinity u, and this will capture every possible point, so if there is a root, we will definitely see it. So given a polynomial p, we will transform from p of 0u to p of infinity u. And maybe instead let's think about evaluating p of ru, where r is the radius, where r goes from 0 to infinity. Now we have to be careful when we're going to infinity. If this is a form of p of x, then this is a form of p of ru, and we see as r goes to infinity, this leading term will also go off to infinity. So we need to adjust that somehow. We can just divide by r to the n, which will then divide all of the terms in the output. For all of the terms on the right, the power of r is higher in the denominator, so as it goes to infinity, they will all go to 0. So we can ignore those. In this leading term, the powers of r are the same, so they cancel each other out, and we just get a sub n u to the n as our limit for r approaching infinity. A sub n times u to the n will be a circle with radius of a sub n that goes around n times, because we're taking u to the n. So this will have a winding number of n. When r goes to infinity, the winding number will be n. But what about when r is 0? Well, here we have a problem, because if we plug in 0 in the top left, we get 0 to the n in the denominator. We can't divide by 0, but we can easily patch that up. We'll just add 1 to the denominator. This doesn't change the result for infinity, but it protects us in the case of 0. So now our denominator is just 1, which means we can ignore it. We just get p of 0u. And so the 0 just multiplies everything out to 0. We just get p of 0. And so when we input 0, all of the terms with an x just go away, and we're left with that constant a sub 0. And so this means our output is a fixed point. We just have some point a sub 0. And this fixed point isn't going around at all, so it has a winding number of 0. So transforming R, we start with a winding number of 0, and we end with a winding number of n. And so these winding numbers are different, so there must have been some radius z between 0 and infinity, such that this equation in the top left equals 0. And if this equation equals 0, the numerator must be 0, which means there is some input for p that gives an output of 0. There is some root. And so we see any polynomial p has at least one root, which is what we set out to prove. This is the fundamental theorem of algebra. But I think it's important now to actually watch this process in action. It's one thing to talk about the technique, but it's great to see how this actually works. So let's take a look at the output for various polynomials. Now, the fundamental theorem of algebra and this proof are quite interesting themselves, but this also leads us to some more questions that I'll explore in future videos. In this process, the winding number started at 0 and went to n. We were only looking for it to change, but we got a change of n, which corresponds to the polynomial having n roots. So there is some connection here. We also talked about this process of going radius 0 to infinity for polynomials, but it'd be interesting to see it for e to the x, or sine of x, using their polynomial approximations. And finally, one of my favorite topics, cyclotomic polynomials have many different roots all on the unit circle, so they make very cool patterns when we put them through this process. That's all for now. Thanks for watching, and stay tuned for more.